go. Here's this important announcement. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, I have a couple of questions requested. This is from section 9.2. First of all, number 37. It says, simplify the expression. The variable represents a positive real number. So we don't have to worry about any absolute value stuff. Okay, so we've got t to the 6/5 power times the quantity t to the 14/5 plus t to the -6/5 power. So distributing, we're going to get t to the 6/5 power times t to the 14/5 power plus t to the 6/5 power times t to the -6/5 power. Multiplying two powers with the same base, you would add the exponents. So this becomes t to the 25th power, which is t to the 4th. Multiplying two powers with the same base, you add the exponents. So this becomes t to the 0 power, which is 1. And there's the final answer. Any questions about that before we go on to the next one? All right. This is also from section 9.2, number 39. Simplify the expression if possible. Assume that the variable can be any real number and use absolute value bars when necessary. Okay. It says a to the 4th to the 1/4 power. Okay. So when you have a power raised to a power, you would multiply the exponents. 4 times a 4th is 4/4, which would be 1. So our answer is A. However, we don't know whether A is positive or negative or 0. And since we're taking an even root, we can't get a negative answer. Therefore, we need absolute value bars on our final answer. All righty. Any questions from any of you before we go on? Well, then we'll go on to section 9.3, and here we go. So I want to remind you of a couple of things, actually 3. You can't take an even root of a negative number, okay? When you take an even root of a positive or 0 number, you can't get a negative answer. And finally, the nth root of a to the n power equals a if a is greater than or equal to 0. The nth root of a to the n equals a if a is greater than or equal to 0. All right. We're going to rely on those 3 rules here. Okay. Now, what we're going to do next is called simplifying an expression. And the name is going to seem confusing because sometimes the simplified version of a problem looks more complicated than the original version. So what do we mean by simplifying? Well, we're going to simplify a radical. And what that means is we're going to take everything that we possibly can and kick it outside of the radical so the quantity inside is the smallest it can possibly be. Let me give you some examples. Okay. Let's say I've got the square root of 4. Well, that's just 2. So simplifying that radical, we pretty much got rid of the radical, right? But let's say I've got the square root of 8. Well, there's a couple of rules that we use in this section, and they're actually the radical version of properties of exponents that we already know. So let's come back to this in just a minute. We have a property that says if you have a product raised to a power, you attach the power to each factor of the product. So for example, 3x, the quantity squared is 3 squared x squared, which is 9x squared. All right. Now, suppose that our exponent was a fraction, 1 over n. Wouldn't this be the same thing as a to the 1 over n times b to the 1 over n power using that property? Okay, let's take this example and let's translate it into radical notation. The nth root of the product AB would be the nth root of A times the nth root of B. So what that tells us is that when we have a product, if the radicand, the stuff inside the radical, is a product, we can pull it apart into separate factors and take the nth root of each, again, each separate factor. Okay, so let's go back to this square root of 8. 8 is not a perfect square, but I could break it apart into a product that's a perfect square times whatever's left over. Okay, then I could rewrite that as the square root of 4 times the square root of 2 using the rule we just looked at. Why would I do that? Because the square root of 4, since 4 is a square, the square root of 4 is a 2 outside of the radical. So the square root of 8 simplified becomes 2 square roots of 2. Now, as I said, the answer looks more complicated than the original problem. So how is that simpler? Well, it's simplified in that the radicand has been reduced down to a smaller number. Any questions about this example? All right, let's continue. Simplify the expression, the square root of 28. What I'm looking for are perfect square factors of 28. Sometimes they're obvious, sometimes they're not obvious. If it's not obvious, what you could do is the prime factorization of the number and say, oh, there's a square plus leftovers. Okay, so doing it this original way, I've got a 4, which then becomes the square root of 4 times the square root of 7, which is 2 square roots of 7. Or doing it this way, you'd say, well, that's equal to that, and the square root of 2 squared is 2, right? Because the index of the exponent, the nth root of a to the n is a if a is greater than or equal to 0. So again, if you can see it, great. If you can't, this is a longer way, but will always get you there to those perfect square factors. Okay, we doing all right? I'll take that as a yes. Next problem, 9 times the square root of 54. Again, simplify the expression. Well, the 9 is already outside of the radical, so we don't need to do anything to it just yet. But 54, let's see, oh, that's 9 times 6, isn't it? 9's a perfect square, so I could rewrite this like this. 6 breaks down to 2 times 3, so there's no perfect squares there. So then this would be 9 times the square root of 9 times the square root of 6. Again, splitting up the product into separate radicals, okay, which is 9 times 3 times the square root of 6, which is 27 square roots of 6. Any questions there? All right. Okay, next problem, the cube root of 40. Our index has changed. Now we're not looking for perfect squares, we're looking for perfect cubes, numbers that are cubes. Well, let's see. 40 is 8 times 5, and 8 is 2 times 2 times 2. Oh, so 8 is a perfect cube. So this would be the cube root of 2 cubed times 5, which is the cube root of 2 cubed times the cube root of 5. Well, the cube root of 2 cubed is 2, and that 2 is outside, so my final simplification is 2 cube roots of 5. Now, again, I went the long way. If you could, in your head, see that, oh, 8 is a perfect cube, and then you could, from there, you could go the cube root of 8 times the cube root of 5, and then what, 2 cube roots of 5. So whether you break it down or can see it, it's up to you. Okay, if you can see perfect cube factors within a number, then great, take advantage of that. How about this? The fourth root of 32. Well, 32 is 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, which is 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power. Now, if the nth root of a to the n equals a, when a is greater than or equal to 0, if my index is a 4, it would be nice if my power or exponent inside the radical was also a 4. So now that I've bunched this together, I'm going to break it back apart and pull off a 2 to the 4th power there. Why? Because the 4th root of 2 to the 4th is 2, and then I've got the 4th root of just 2 left over inside. Okay with that? See what I'm doing there? Again, if you know that 32 is 16 times 2 and 16 is something to the 4th power, great, but my guess is most of us won't. So this way will get us there. Okay. Now we're going to introduce some variables into the situation. Simplify each radical expression. All variables represent positive real numbers. That means we don't have to worry about absolute value bars within this mini section here. All right, well, 50 is 25 times 2, and 25 is a perfect square. So I could rewrite this as 5 squared times 2 times x squared. Okay? So I've got squares and the leftovers. Now, I want to shortcut this process a little bit, but first I'll do it the long way that I've been doing it. Okay, so the square root of 5 squared is 5 outside. The square root of 2 is stuck inside. The square root of x squared is x. So I get 5x square roots of 2. Okay, now a shorter way of doing this would be to say, well, since this is a product, I'm just going to go through and say, oh, that's going to be a 5 outside. The 2's stuck inside. That's going to be an x outside. And I'll do it like that. Okay. So if you need to, you can do it this way, but you could also do it that way. Just keep track of what you're doing. Okay, let's see here. The square root of 75, b to the 8th power c. Now, 75 is 25 times 3, which is 5 squared times 3. So I've got 5 squared times 3. Oh, b to the 8th is b squared times b squared times b squared times b squared, and then times c. Okay, don't panic. I'm going to shortcut this in a minute, but I want to do it the long way first. So everybody okay with how I got from here to there? Any questions there? Okay. And again, why did I break the b to the 8th up into b squareds? Because my index is an implied 2, right? So the square root of 5 squared is 5 outside. The 3 is stuck inside. The square root of b squared is a b outside. The square root of b squared is a b outside. The square root of b squared is a b outside. The square root of b squared is a b outside. And what have I got left inside? 3c. So I've got 5b to the 4th square roots of 3c. Now that's doing it the long way. Let's go back and shortcut this process. Let's just focus on that. Okay. Now, I could break b to the 8th up into b squared times b squared times b squared times b squared. But if the exponent here either matches the index or is a multiple of the index, I can do it even quicker. Consider this. And usually the 2 isn't written there, but in this case, I wrote it there. Isn't this the same thing as that in exponential form? So if this number is a multiple of that, I just take this divided by that, right? So what does that mean? Well, I could take this and I could say, okay, that's 5 squared times 3 times b to the 8th. I'm going to leave it as an 8 because that's a multiple of the index. Okay, so now this is a 5. This is going to be b to the what? 8 divided by 2 is 4. And then I've got 3c left inside. Okay, because this is going to get old if it's like b to the 48th power. You're not going to want to sit there and write b squared 24 times. Okay. Any questions about that process? Okay, let's see here. We have 4 times the cube root of negative 81 a cubed. All right, so now I've got a cube root. That index tells you what you want. So I want cubes. Well, negative 81 is negative 1 times 81, which is negative 1 times 9 times 9, which is negative 1 times 3 times 3 times 3 times 3, which is negative 1 times 3 to the 4th. Okay. Now, 3 to the 4th, I'm going to write as 3 to the 3rd times 3 to the 1. And that 1, I don't really need to put it there, but I'm just putting it there to remind you where it came from. Negative 1, this is one that kind of stumps people because negative 1 cubed is negative 1. So negative 1 is in fact a cube, and the cube root of negative 1 is negative 1. So here's what I've got. I've got 4 times the cube root of negative 1 times 3 cubed times 3 to the 1 power times a cubed. So I've got a 4 outside. What's the cube root of negative 1? That's a negative 1. People forget to take that negative outside. The cube root of 3 cubed is a 3 outside. The cube root of a cubed is an a outside. And what have I got left inside? I've got the cube root of 3. So 4 times negative 1 times 3 is negative 12. And then a times the cube root of 3. Okay. Let's see here. Now, I've had people in the past nail this next test, get 100% except one minute detail. They'll have a problem like this and they'll forget to put the index there. Okay. If it's a 2, it's implied if you don't put anything there. But if it's anything other than a square root, you've got to put the index there. Okay. And in WebAssign, you know how you click on the box and then over on the right side, there'll be a bunch of stuff that opens up that you can go in and deal with. So there'll be, I think there's a box where it looks like this, and you'll be able to put whatever index goes in there. So be careful to watch for that situation. Okay. All right. How about this one? The 5th root of 64, x to the 10th, y to the 5th. 64 is 8 times 8 is 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th, which is 2 to the 5th times 2 to the 1. So I shoved it all together and then I pull it apart into 5th powers and leftovers to match my index. X to the 10th, 10 is a multiple of the index. Y to the 5th, 5 is a multiple of 5, 5 times 1. So 2 to the 5th times 2 times x to the 10th times y to the 5th. All right. 2 to the 5th, take the 5th root of it, you get a 2 outside. X to the 10th, take the 5th root of it, the 5th root of it, you get x squared outside. Y to the 5th, take the 5th root of it, you get a y outside. And what's left inside? You've got the 5th root of 2. See how it's working? match the index or a multiple of the index, kick it out, and then whatever's left over stays inside. Okay. Simplify each radical expression. All variables represent positive real numbers again. The square root of 363. Okay, let's see, 363. Remember the rule to tell whether 3 goes into a number? If you add up the individual digits of the number, so 3 plus 6 is 9, plus 3 is 12. If 3 goes evenly into the sum of the digits, 3 goes into the actual number. So this is going to be 3 times what? 121. Okay. And 121 is 11 squared. So I've got 3 times 11 squared. My index is a 2. I want squares. Okay. Square root of 3 stuck inside forever. Square root of 11 squared is going to be 11 outside. And I've still got the square root of 3. So 11 square roots of 3. Okay, let's see. How about this one? Negative the 7th root of 256 t to the 6th power. 256. Let's see, that's 2 times 128, which is 2 times 2 times 64, which is 2 times 2 times what? 8 times 8, which is 2 times 2 times, and then 8 is 2 times 2 times 2, and 8 is 2 times 2 times 2, and I've got 1, 2, what? 2 to the 8th power, which I'm going to write as 2 to the 7th power times 2 to the 1 power to match my index. So I get this, the negative, the 7th root of 2. Oops, I messed up, made a mistake there. There we go. Okay. 2 to the 7th times 2 to the 1. So I've got 2 to the 7th times 2 to the 1 times t to the 6th. The 7th root of 2 to the 7th is 2 outside. Don't forget that negative sign outside. And that's it, because t to the 6th, if the exponent inside is smaller than the index outside, then I can't do anything with it. So negative 2 times the 7th root of 2t to the 6th power. Final Jeopardy answer. All righty. Now, something that I did, I think, back in section 9.1, but never really explained myself that much. I said something like, let's say you got the square root of 4 over 25. I said that you could split it up like this, and then do each, the numerator and the denominator separately. Let's take a look at why that's legal and what rule comes from that. So again, let's go back to properties of exponents. We have a rule that says a quotient raised to a power, you attach the outside power to both the numerator and the denominator of the quotient. So if I've got 2/3 to the 4th power, that's 2 to the 4th over 3 to the 4th, which is 16 over 81. Okay. Well, what if I had a over b and my exponent was 1 over n? Wouldn't that give me a to the 1 over n power divided by b to the 1 over n power? What if I take that last statement and convert it into radical notation? The nth root of a over b is the nth root of a divided by the nth root of b. So not only can we take a product inside of a radical and pull it apart into separate factors, we can take a quotient inside of a radical and separate the numerator from the denominator and take separate roots of both. Okay. So let's say I've got the square root of 3/4. That can be split apart into the square root of 3 over the square root of 4. And the square root of 4 is 2. The square root of 3 is irrational. Can't simplify it exact. how about this one? The fifth root of 2 divided by 243. That's the fifth root of 2 over the fifth root of 243, which is the fifth root of 2 over, let's see, 243 is 3 times 81, 3 times 9 times 9, 3 times 3 times 3 times 3 times 3, 3 to the fifth power, the fifth root of 3 to the fifth. So what have I got? The fifth root of 2 over, what's the fifth root of 3 to the fifth? It's 3. So my final answer, the fifth root of 2, or yeah, the fifth root of 2 over 3. Okay, what about this? The sixth root of 5y to the 12th over 64. So that's equal to the sixth root of 5y to the 12th over the sixth root of 64. Well, the sixth root of 5y to the 12th, I can't do anything with the 5, but the sixth root of y to the 12th would be what? Y squared on the outside. So I've got y squared times the sixth root of 5. Okay. Now 64 is 8 times 8, which is 2 times 2 times 2 times 2 times 2 times 2. So that would be the sixth root of 2 to the 6th. And the sixth root of 2 to the 6th is 2. Final answer, y squared times the sixth root of 5, all divided by 2. Any questions there? Now, not only can I take a fraction inside of a radical and pull it apart, if I have a fraction that's already written, let's see here, like this. If the indexes, I don't know if the plural of index is indices or what it is, but if they're the same index, I could go the other direction, which sometimes is quite convenient. Okay. Any questions about that? Let's say I've got this one. Okay. Or how about this one? So it's kind of like an accordion. You can pull it apart, you can push it back together. Any questions there? Okay. Let's see here. Let's do one more of those. Let's say you've got the cube root of 243 x to the 8th over the cube root of 9x. That's the cube root of 243 x to the 8th over 9x, which is the cube root of, let's see, 243 divided by 9. That's what, cube root of 27, and x to the 8th divided by x would be x to the 7th. Okay. Well, 27 is 3 cubed, and x to the 7th. Oh, 7 isn't a multiple of 3, but what's the largest number that is a multiple of 3 that's less than 7? 6. Okay. So I'm taking x to the 7th and writing it like that, pulling off x to a power that's a multiple of 3. Okay, so cube root of 3 cubed, 3 outside, cube root of x to the 6th, x squared, cube root of x. So 3x squared cube roots of x would be my final answer. Okay, one more I want to do, and then I'm going to look at something a little bit different. What if I had the cube root of 81 x to the 14th y to the 8th power? Okay, how would I deal with that? Well, 81 is 9 times 9, which is 3 times 3 times 3 times 3, which is 3 to the 4th. So I'd write that as 3 to the 3 times 3 to the 1. Okay, and I can put the 1 exponent or I can leave it either way. X to the 14th. What's the highest number that's a multiple of 3, but 14 or less? Wouldn't it be x to the 12th? So that's going to give me x to the, x to the 12th times x squared. So 12 is the highest multiple of 3, less than 14, and I've got an x squared left over. Y to the 8th would be what? Y to the 6 times y squared. So inside the radical, that radicand, I'm breaking it apart into powers that are either a 3 or a multiple of 3, like a 12 or a 6. Okay, so this stuff is going to go outside, and this stuff is going to be stuck inside. Okay, the cube root of 3 cubed is a 3 outside. The cube root of x to the 12th is x to the 4th outside. The cube root of y to the 6th is y squared outside. Left inside 3x squared, y squared. Don't forget that index. How are we doing? Everybody okay with this?
Yeah, I'm good.
I know I'm probably sadistic, but I think this is fun. What can I say? Sorry. What? How dare you, Mr. Mayo? Okay. Now, we've talked about simplifying radicals. We're going to look at combining like radicals, kind of like terms. In other words, what's 2x plus 3x? Well, that's 5x, right? 2x plus 3x plus 4y would be 5x plus 4y. These are like terms. These are not. Okay. What if I had 2 square roots of 5 plus 4 square roots of 5? Wouldn't that be 6 square roots of 5? Okay with that? So those are like radicals. Okay. So we're going to combine like radicals. But sometimes radicals are alike, but we don't see it looking at them initially. So the key to this whole thing is we're going to take each separate term and we're going to simplify the radicals and then see what we've got. Okay, so first of all, hopefully some obvious ones. 11 square roots of 3 plus 2 square roots of 3 would be 13 square roots of 3, right? And 30 cube roots of 6 minus 10 cube roots of 6 would be 20 cube roots of 6. But what about this problem? 9 plus the square root of 45 plus the square root of 20 plus 16. Well, the 9 and the 16, those are like terms, so we could combine those, and we'll do that in a minute. But the square root of 45 and the square root of 20 don't look like they're like radicals. But let's simplify each one. Okay, now 45 is 9 times 5, 9 being a perfect square. 20 is 4 times 5, 4 being a perfect square. Okay, so now I've got 9 plus, oh, the square root of 9 is 3 left outside, and the square root of 5 inside, plus the square root of 4 is 2 times the square root of 5 inside. So now what have we got? Those are alike. So that's what? 25 plus, and those are alike. 5 square roots of 5. So again, the secret, simplify each radical first, and then see if they are like radicals. Now, don't assume that all the radicals are going to simplify down to where they'll all be like radicals and combine. Sometimes they do, sometimes they don't. Okay, let's see here.
So would the 5 square roots of 5, that would be the simplifiedest version for that?
Yes. Now the whole answer includes the plus the 25, but yes, because the square root of 5 inside, you can't take it outside. It's not a perfect square.
Okay.
Does that make sense?
Yeah, it just, since it all ends in 5s, it
Oh.
looks like it could be
Yeah.
simplified.
Yeah, coincidence. I know. And these are not like terms because this one doesn't have a radical, whereas this one does. Okay. All right. Consider this. The square root of 80m minus the square root of 128m plus the square root of 288m. Okay. So I've got 3 radical terms. I'm going to simplify each separate radical as much as I can. 80, let's see. Oh, what's a perfect square that's in that? 16. Now, if you didn't see that, you could break 80 down into prime factors all the way down, and you'd get 2 to the 4th power times 5. Okay. So this would be 16 times 5 times m, which becomes 4 square roots of 5m. Okay, so far? So I simplified that radical as much as I could. Minus 128 is 2 times 64. And let's see, the square root of 64 is an 8 outside, and left inside is the square root of 2m. Okay. So already I've got 2 simplified radicals that don't match, do they? Plus 288 is 2 times 144. 144 is 12 squared. So the square root of 124 is 12 times the square root of 2m. So I've simplified the 3 radicals, but only these last 2 are alike. So I've got 4 square roots of 5m plus 4 square roots of 2m, because minus 8 plus 12 is plus 4. You see that? Okay. Let's do one more here. How about this one? The square root of 20 plus the square root of 125 minus the square root of 80. 20 is a square times 5. 125 is a square times 5. And 80 is a square times 5. Now, does anybody want me to go back and do it the long way and break it down to show where I got it? No one cares. It's Friday. They just want me to shut up so they can go back to their life. All right. Square root of 4 is 2. Let's slow down. Square root of 25 is 5. Square root of 16 is 4. These are all like terms, aren't they? Like radicals. 2 of something plus 5 of something is 7 of something, minus 4 of something is 3 of something, the something being the square root of 5. And there you have it. And Bob's your uncle. Any questions? All righty, so for the weekend, you've got section 9.3. I'll be back at 1:15 with an office hour. Should you have any need of me, and I'm going to stop the recording.